Hello everyone, John here. Today we're going to be talking about the double slit experiment. Very famous experiment, very widely known. Many physics enthusiasts know about this experiment. So I'm not going to go into great detail about the experiment itself. I'll put a link on in the description to PBS Spacetime's video about this experiment, which is actually an excellent video where Dr. Matt Dowds talks about it. And there are also numerous videos on YouTube if you actually want to do the experiment yourself. It's not hard. It's not a hard experiment to do. Safe, um, and it also provides great insight to some of the fundamentals of quantum mechanics. So this experiment right here is was big in developing the concept of wave-particle duality. So in this experiment, in the picture right here, we're looking at a light source. We're looking down from the ceiling to the floor, and with the light waves propagating towards a wall that has two apertures in it. And the waves propagate through the apertures, and then as separate waves, they come out and interfere with each other, and they develop an interference pattern on the back wall, and that's what we're going to look at. So what's happening here is this experiment shows that light propagates as a wave, and when we say wave particle duality, even a single photon propagates as a wave. And if we were we were to run this experiment, I mean, I know you can easily think of a flashlight. When you turn it on, you have all these photons rushing out. Some of them going through one side, some of them going through the other. But and then they're interfering with each other. But that's not what's going on. If you were to run the experiment with a single photon, and let's say you fired one every 10 seconds, for however many hours or even days, um, after you finish the experiment, you would still end up with the same interference pattern as if you turned on your flashlight or your laser. So and so what that's showing is that even a single photon, or it is the single photon that is propagating as a wave and going through both slits, not as a particle, but as a wave, just like water waves. When you drop a pebble, you see the water rays propagate along the surface of the water. That's essentially what's happening here, and that's a whole branch of physics that's a very advanced and very accurate branch of physics that goes into the fields. Um, but for what we're doing right now, we're going to stick to the basics. We're going to look at some of well, not this code right here. We're going to look at some of the graphs that we have down here to see what's going on with the light as it's propagating through the apertures and landing on the back wall. And the wave equation that I'm using is down here. It's a very simple form of the wave equation. I'm not using any units or nothing to actual scale or anything like that here. We're uh, we're using the equations just to plot the graphs and kind of show the concepts of what's happening. If we look up here um, at the top left graph, what we'll see is right now we have a single aperture open, and so imagine you shining a light through a small hole, and then the lights propagating to the other side, and it's what you would normally see down here at the bottom light. You have a bright spot in the center, and then as you move away to the left and right, the intensity drops off. So this is a normal case of what you normally see, what you think of when you kind of turn your flashlight on and you see the bright spot in the center of the wall. And so we have in the top left quadrant in this graph, we have concentric circles moving away from the aperture that is open at the moment, the first aperture, and if you if you recall, the plane wave equation is usually in the form of the Euler number E to the ikx, where I is the imaginary number, and when we have that form, it's going to give us complex cosine functions, and that's what we're seeing here for the wave function. And imagine the light parts of the circles being your uh, your amplitudes, your heights, and the dark parts, your troughs, your depressions of your cosine wave as it propagates out from the aperture. You see a little bit of distortion here. That's simply because the working precision of my computer. And even as we go through here, I'm crossing my fingers, hoping that it holds up. But we're looking good so far. And then down on the graph in the bottom left, this is the probability amplitude, which is the magnitude of our wave equation squared. So this is a real function, not a complex function. So we no longer have the cosine, but this is the actual probability density that gives us our light intensity. Follows the same pattern as a light intensity, where right at the aperture, we have high intensity, as we see in the top right quadrant, and on our graph, or yes, our graph at the bottom right, as we're looking at our wall. So if we look back over here, the bottom left quadrant, from our aperture, our light, the most of the probability of the light is centered right at the aperture, and it drops off as you move away. And so that's what we would expect in a normal case. And now we are going to turn on our second aperture to see what happens. And let's give it a second to think, and hopefully we'll get a good interference pattern here. Yes, this is exactly what we want. So now in the top left, we see our wave functions interfering, and as they propagate, we see how the concentric circles are interfering, forming another pattern, and the probability density down on the bottom left, it's kind of like light rays shooting from the center of the two apertures, and so that's the constructive interference of those concentric circles that causes that. And then when we look at our intensity on the right, so it matches exactly with our probability density. So we see a good interference pattern that matches the graph right above it. Both graphs on the right match each other, and then if we look at the intensity on the bottom right, and then we look at the graph on the bottom left, imagine the wall being the top, and everywhere these points of constructive interference touch that wall corresponds to a point of brightness on the bottom right graph. And you can kind of see that the center touch is very bright, and you can see these lighter yellow spots as you go out would be a little less bright, and that's exactly what's happening in our interference pattern. Now we have one more to look at, and we're going to separate them a little bit more. Separate our apertures. So now our apertures are going to be further out, and when that happens, the further away they get, now the less interference that we're going to get, because they're going to be too far apart to interfere in that manner to give us that interference pattern. So now we kind of see our light intensity is just the normal, two bright spots. They're still close enough you can kind of see a small bright spot in the center. It's not completely dark. And on our probability density graph at the top right, we kind of see, you still have some amplitude in the center, and then most of your brightness is right in front of the apertures, like we'd expect. So that's that's the basics of what's happening with the wave functions. There's a lot more to it. This experiment actually also works with only one slit in certain cases because of the boundary conditions at the edge of the slits. Actually, it works in the same manner because of diffraction. You get this similar interference pattern, and you can actually do the same thing with a single slit. You can do the same thing um, if you have a thin metal sheet. The edge of the metal sheet can kind of act as your boundary, and you can get a diffraction pattern. And so there's other things that are going on with the wave function that's not covered here, but you can see um, you can see the wave particle duality of the photon and its effects and how this kind of changed everything that the way that we were thinking about particle physics. So that's all I got for you guys today. I hope you enjoyed the video. This is a good proof of concept for me with the program because I've been working with Mathematica for a little while. I'm just trying to go through and see what I can do with it. So thank you guys for watching, and I'll see you next time.